This is why I'm never gone, because it's so much work. Anyway, it's so much easier just to be here. All right, so I'm going to kind of take you through the lab. So there's two distinct parts to the lab. The first part is going to find the molarity of this sodium hydroxide. So what we're going to do is we're going to use this reaction. This is the full-blown equation for KHP. Potassium, hydrogen, phenol, something, I don't even remember. And quite frankly, I'm too tired to even think. Anyway, so here's going to be the basic idea. This is going to react with sodium hydroxide, and basically it's a really, really complex double displacement reaction. So what's going to happen is that, obviously, that's aqueous sodium hydroxide. So what's going to happen is the sodium is going to come in here, and it's going to kick out the hydrogen. So when it kicks out that hydrogen, it's going to bond with that remaining OH, and you're going to produce water. Then, as that gets kicked out, that sodium takes that place, so you get this complex ion over here. So, but here's what's going to be important. Everything is in a 1-to-1 ratio, so the stoichiometrics going to be easy. The reaction is going to go until this KHP is used up. Once the KHP is used up, then if you add any more sodium hydroxide, the solution is going to be basic. So what you're going to do is that I've got the 4-digit electronic balances over there, and you're going to measure out KHP. So you're going to do 3 trials. Now, if you're the Thursday group, you're going to do 2 trials. You're going to measure out about 0.4 grams. That's going to be trial number 1. So you're going to take 0.4 grams, and you're going to pour it into a 250 milliliter beaker. And then, and this is going to be important, you're going to record that mass on this sheet where it says mass of KHP, right here. You're going to, so that's going to be like 0.4 something. So, moles of KHP, you're going to divide that by the molar mass, which I'll get to in just a second. Your final burette reading, milliliters of sodium hydroxide used. So we'll get to those numbers in just a second. So, here's what's going to be important. You're going to measure out that 0.4 something grams. You're going to record that. And don't sit there and go and spend 5 minutes trying to get this exactly at 0.4. As long as it's something close to 0.4, okay? That's all you have to have, just something close to 0.4. And then you're going to add, and when you read the lab, this is important. It says you're going to add 100 milliliters. Now, notice that this is written without a decimal place. So in other words, you're going to add about 100 milliliters, okay? You got a 50 milliliter graduated cylinder, fill it up twice. This doesn't say 100.0000, okay? It's just about 100. So this is what's going to be important. The volume of the water that you add isn't going to be part of the story. The only thing you're adding the water to is to get the sodium, is to get the KHP to dissolve. That's all you're going to do. Okay? That's it. So you can have about 100 milliliters of water. You're going to add the KHP. Let it sit there. It's going to dissolve. Okay? And you've got, hopefully you all are familiar with these. You're going to have, hold on. These squibs, okay, right? And they've got like a little magnet on them. When you turn them on, they spin, okay? So you're going to put that in here, add your KHP, add the water, put it on there. Now, hold on. It's been a bad day, by the way, or at least a long day. All right. So at this point, you're going to add 2 or 3 drops of phenolphthalein. They're going to be in your little black tray at your table. Add the phenolphthalein. So remember, phenolphthalein turns magenta when it becomes basic. So what you're going to do then is that in your burette, now let me move this in here, so now we can talk about this. Okay? So you're going to have a ring stand like this, right? If you've never worked with these before, loosen that clamp. There's your 50 milliliter burette. And the first thing that you need to do with this burette is run a bunch of water through it so that it doesn't get seized up like this is. Okay, assume that this can turn. Somehow or another this got froze up. Okay. I'm not going to try and fix this right here, right now. Okay. Anyway, you can turn this valve on and off on normal ones that actually work. I happen to grab the one that's locked in place and I can't get it to turn. But imagine this can turn. You all have imaginations. Imagine this can turn. So what you want to do is run through distilled water. Do not wash this with soap. Okay? Do not wash this with soap. Just rinse it through with some distilled water. Then, when you get done with that, then you actually want to rinse it with some sodium hydroxide. Now, in the lab, you're going to see that these are numbered, okay? Like 1, 2, 3, and 4. Whatever number you use, stick with that number, okay? You want to write that down on this piece of paper somewhere. Like, you want to write down, hey, bottle number whatever, because that's going to be important later on. So make sure that you use whatever bottle you start with, keep drawing from that. Now, don't be a caveman chemist. Don't take this whole bottle back to your lab station and pour it in from there. What you want to do is take a clean beaker, because you can only put 50 milliliters in here. Take a smaller beaker, pour some in here, take that back with you to your lab station. Don't be a caveman chemist where you're going, I'll take the whole bottle with me. No, because then everybody else gets upset. So don't take the whole bottle with you. Take a beaker, make sure it's clean, pour some into there, then take a funnel, okay? Take a funnel, put that at the top, pour that in there, rinse it thoroughly with sodium hydroxide before you start the trial. Then what I would recommend is that you fill it up here to the top, okay? So you're going to fill it back up there to the top. Remember, when you're reading a burette, you read from the meniscus. So you read from the bottom. When you look at this, you're going to see a noticeable curve because of the properties of water, and it sticks to the side. Read from the bottom. So I would fill it up to there. So what you're going to do, when you're trying to find your KHP concentration, I would add like 2 milliliters at a time, okay? You're not going to keep track of the pH in this trial. You're just going to run this a couple milliliters at a time, and so you're going to be pouring that sodium hydroxide into this beaker. So use your imagination. Imagine you have your KHP in here with 100 milliliters of water and the phenolphthalein. Make sure that you add the phenolphthalein. Then you're going to be adding sodium hydroxide to it, and what you'll see is that as it gets closer to the end, what you'll see is that magenta color stays a little bit longer each time. Okay, it just stays a little bit longer. So when you do this just right, you're going to add, like, literally, as you get closer to the end and that color lasts longer and longer and longer, back that off and add smaller and smaller and smaller amounts of sodium hydroxide. Because what you want to do is you want to get it to where you add just 1 drop and then that stays magenta. So when that happens, you have used up all of the KHP, then you have excess sodium hydroxide ions in the solution. That's what makes it basic. So as long as there's KHP here, the sodium hydroxide gets reacted. As soon as this is gone, the solution will go basic, and then you'll get that magenta color. So if you do this right, it will come down to like that last drop. It turns it magenta, that color stays, that's when you're at the end point. But if you're continuously adding 2 milliliters at a time, it's no Gouda, okay? You're going to blow right through it. So this just takes a little bit of practice, but you'll see. When in doubt, err on the side of caution. All right. So here's the deal. So here's what you're after is the reading on how much the molarity of your sodium hydroxide. So let me move this out of the way so you can see the board. Now, I've also got this written up there on the board in the lab. This is all written on there, so if you don't write this down, it's written over there in the lab. Don't worry about it. So, you're going to start with whatever mass of KHP that you have. 0.4, 5, 3, whatever your mass is, okay? You're going to convert that into moles of KHP. Here's the molar mass of KHP. Okay, here it is. You don't have to calculate it. I've given it to you. I'm a nice guy. So that's 204.2 grams per mole. There's a 1-to-1 ratio of moles to sodium hydroxide, moles of KHP to sodium hydroxide. So basically, you're going to take this mass divided by 204.2. That's going to give you the number of moles of sodium hydroxide. But you want molarity. Then you're going to take that and you're going to divide that by how much sodium hydroxide came out of that burette. Okay? That's the whole thing. So this is why you have to have, when you do your burette, you have to have like that initial reading on that burette and then that final reading on that burette, and the difference between those two is going to be that volume. It's going to be in milliliters, divide by 1,000, get it into liters. So hopefully this molarity should work out to be something around 0.1, okay? Ballpark is going to be something around 0.1. Now, but here's what I want you to look at. You've got like 4 significant digits in this milliliters, because if you look at the divisions on there, you're going to have 4 significant digits here. You're going to have 4 significant digits in your measurement of mass. You're going to have 4 significant digits in the molar mass. So when you do this conversion into milliliters, count them. I want 4 significant digits. 4. 1, 2, 3, 4. So what you're going to do is that on this side, so my Thursday group, listen to me. I want you to do trials 1 and 2. So you're going to do this twice. Up here, write down which bottle that you had so that I know which data that you've got. And then you're going to calculate molarity. I don't want to have to show every calculation on all 3 trials, but I say show one calculation for trial 1 to obtain molarity, labeling every value. So right here, I want to see this conversion so that I know you know what you're doing. Now, don't worry about trial 3. On Friday, my Friday group is going to do the 3rd trial. You just have to do trials 1 and trial 2. So when you do trial 2, instead of having 0.4 grams, you're going to start with about 0.5 grams. Okay? And then you're going to run through it again. Make sure I would fill this burette back up to the 50 milliliter mark. You don't have to, but I would. That way you know you're starting at the full mark every time. You're going to add that, drop that down. Now obviously, if you have 0.5 grams, that's going to take you more volume of sodium hydroxide than the 0.4 did. So, but again, you can have an idea. So then on Friday, my Friday group is going to do 0.6 grams, and that's where we're going to get the 3rd trial from. Okay, so we're good with that. Once you get that done, here's the next part of the lab. Now we're going to try and figure out the molarity of the acid. So, you're going to take 25 milliliters of acetic acid. So again, you're going to have a bottle in there, and it's going to be numbered. So like, this is acetic acid. The idea is that you're going to try and figure out what's the molarity of this acetic acid. That's your goal. What's the molarity of this? Now, at this point, here's your reaction. It's going to be sodium hydroxide plus acetic acid is going to yield water and the sodium ion and your C2H3O2. Now, what we're only going to worry about, okay, is the net ionic equation. And the net ionic equation is going to be hydroxide plus that acid yielding water and the anion. This is the heart and soul of what we're worried about. I don't care about the sodium. It's a spectator ion, okay? I could care less. This is the heart and soul of what I'm worried about. Now again, here's what's important. This is a 1-to-1 ratio. Now, this becomes much more technical in terms of your technique. So let me load this back up. Actually, I'm going to stop that. I'm going to go get a volumetric pipette. I'll be right back. I thought I grabbed everything. Okay, so you're going to need 25 milliliters of this acetic acid. And again, here's the cardinal sin. Do not take this 25 milliliter volumetric pipette, which is going to be on your table, and draw it directly out of here. Cardinal sin. Because here's the reason why. If this is contaminated, you have now contaminated this entire stock solution bottle. So what you want to do, again, don't do the caveman chemist. You want to pour this out into a beaker. Obviously, you're going to need 25 milliliters. I'd maybe pour out like 40, something like that. You're going to take the bulb filler, which we showed you how to use, and you're going to fill this thing up to this mark. So you're going to know exactly the volume of your acid, okay? You know that's exactly 25 milliliters. So you're going to take that, you're going to pour that into this beaker that you have thoroughly rinsed out, okay? Thoroughly rinsed out. Don't have that sodium hydroxide solution in here. Rinse this completely out. You're going to have this, you're going to put 25 milliliters into here. You don't know the molarity of the acid. So, now, let me pull this up here. Like so. So, you're here. You got the squib. You got this. Now, at this point, you're going to need your pH probe. So, I've got the Lab Quest in there. There's your pH probe. Make sure, for all that is holy, that you don't let this like turn upside down, okay? So all you have to do is unscrew the lid, okay, like so. And then you can pull this, that squeegee up like this. Now, you need a utility clamp. There should be one in your drawer. And you want to hold that in here like this. So, now, there's something that you want to do. You want to make sure that you rinse this off with distilled water before you put it in your solution. Otherwise, this is a buffered solution. Thank you, Amanda, and by the way. I think you did. I think that's who did it. Anyway, so rinse this off with distilled water. I don't have any in here, but rinse this off with distilled water before you put this in here. So you're going to put this in here, okay? And you're going to have that like off to the side because you don't want that magnet spinning and hitting this. So you're going to have this. You have about 25 milliliters in here. You've got your sodium hydroxide up here, again filled up to this. Now, what you want to do is that, now, my Thursday group, you're only going to do one trial with this. First determination. So you're going to have milliliters of sodium hydroxide in your pH. The first thing that you want to record is 0 milliliters of sodium hydroxide, and you want to record the initial pH of your acetic acid, okay? That's vital. Record the initial pH of your acetic acid before you add any base to it. Now, what you want to do is that you want to add like 2 milliliters at a time. So you're going to add 2 milliliters of your base, let that react, record the pH. Add another 2 milliliters, record the pH. So for about the first 10, so you're going to go 2, 4, 6, 8, 10. Record the pH after each one of those. Then I'd start going by ones, and then I'd go like 11, 12, and I would do that probably till you hit about 16, okay? Once you hit 16, then I'd start going in really small increments, okay, like maybe a half, maybe a couple of drops, something like that. Because what you're going to see is that your pH versus volume curve is going to be pretty gradual, and then it's going to make this huge spike, and then it's going to level off. What you'll see later on is that it's vital that you get this data right here, and literally, and you'll see this, 1 or 2 drops once you get to this region will shift this pH by maybe 1 or 2 points. Up to this point, your pH might only change like a couple of tenths, But once you get close to this critical stage, if you blow through this, it's very easily to do. You have to start all over. Again, err on the side of caution. So I'd go like 2, 4, 6, 8, 10, okay, record those. Then I'd start backing it off into individual milliliters, recording the pH. Once you hit past 16, then crank it down. Now, once you get through this spike, then you can go back to adding 2 milliliters at a time. I don't care what happens over here, so once you hit through this big spike, get 3 or 4 more readings, call it good, okay? So, 2 milliliters, crank it down, drop, whoop, get the spike, whoop, go back to 2 milliliter increments, okay? Now, if you want to, I don't care what indicator that you can use. If you want to use phenolphthalein as your indicator so that you get a visual idea when it's getting close to being basic, that's fine. If you want to use universal indicator, that's in your tray as well. I don't care which one you use, pick one. So you're going to have 2 ways to see what's happening with the pH. Your pH probe and that visual indicator, whether it's phenolphthalein or universal indicator, I don't care, pick one. Now, here's where math kicks in. By the way, I forgot to mention this. Make sure when you're doing this bit with the KHP, that 100 milliliters of water, make sure that that's that water that you boiled on Monday. Make sure you use that boiled water so that you don't have carbonic acid in your solution. Okay, back to our story. So, so tomorrow you're going to get this. You're going to have, if you want to go ahead and plot this data, you can. So what's going to happen is that you're going to have this pH curve. So this is why it's so critical that this data is right. Because initially, for now, you want to find like the midpoint of this curve. So imagine like you're drawing like a tangent line straight down. And there is no shortcut way to do this. You just have to plot the points and find the middle of this mark. Drop that straight down. This is what we call the equivalence point. Okay? So that right there is what we call the equivalence point. That's going to correspond with some volume. I'm guessing it's going to be somewhere around 20 to 25 milliliters. Okay? Something in that ballpark is about where it should be. Okay? That's a ballpark. Okay? So, but you don't know that until you get all of these points plotted on your graph. So, once you get that equivalence point, that's going to tell you the volume of your base. Now, here's what's important. At that point, you're going to know the volume of your base, and you're going to know the molarity of the base. So, there's a handy-dandy little equation, and again, this is on the board in there. You can go MAVA equals MVVB. So this is basically, what we're saying is that the moles of acid, molarity times the volume of the acid, is going to equal the molarity of the base times the volume of the base. Moles of acid equal moles of base. And the only reason we can do that is because everything is in a 1-to-1 ratio. If we had like coefficients of 2 or 3, we can't do MAVA equals MVBB. But because everything's in a 1-to-1 ratio, we can. And this doesn't matter that this is a weak acid. Doesn't make any difference. Does not matter. Hold on. Sorry about that. My meal got delivered at 6:30 and I haven't left this, basically haven't left this room all day. Okay. Anyway, now my marker is gone. Hold on. It's been a day, kids. By the way, you'll see this on the posters. My Bernie Sanders mittens. How cool are these? Huh? Here, I'll give you the look. Yeah. Okay. So, pretty cool. That was kind of random, but anyway. So, you're going to use this equation. What you don't know is the molarity of the acid. So, So what you're going to do, this is going to be the molarity of the base. You don't know this number yet because you don't have the third trial, but this is just going to be the big idea. So you're going to have the molarity of the base, which you're going to get on Friday once they do their trial. Then you'll be able to calculate the molarity of the base. You're going to know the volume of the base, because that's going to come from the midpoint of this pH curve. So you're going to know this number. You're going to know the volume of the acid, so that's going to be 25 milliliters. Okay? The only thing you don't know is the molarity of the acid. So this is going to be the big calculation that you're going to do the following day. So the reason I'm just going to point this out is so that you see the importance when you generate this pH curve, that you find this, you have to have this data just right. You have to have a whole bunch of data sets in here so you can find the exact midpoint. Now, my Thursday group, this is what I want you to get done. I want you to do 2 trials with the KHP, and then 1 trial with this. My Friday group, you're going to do the 3rd trial with the KHP, and then you're going to do 2 trials with the acetic acid. My Thursday group, if you have time, you could go ahead and do your own 3rd trial with the KHP and have that knocked out. If you don't worry about it. Now, here's what's going to be important. Listen to me, I want a member of each group, okay, listen to me, my Thursday group. I want a member of your group to take a picture of this page, okay, right here, the standardization of sodium hydroxide solutions. I want you to take a picture of this so that I have that, so that I can share that with my other group. Here's the other thing. Then, when this first trial, I want to take a picture of this. So this is your sodium hydroxide and pH. I want a picture of this, okay, so that I can share that. Who's ever doing this, write neatly and darkly so that, and legibly, so I can read this. So when you take a picture of it, so email it to me. I want a picture of this page with your 2 trials, a picture with this page with this trial. Okay, peace out. I'm actually going to take time to eat right now. So if you have any questions, talk to Mr. Schertz or Ms. Utt, and they know the drill. So literally, if you have any questions, ask them. Okay.